is the second derivative 0? X is negative 1/4, right? Negative 1/4. Is the second derivative ever undefined? No. So I only have one solution here. And so if I were to take this on a number line and put negative 1/4 here, it would break up my number line into 2 sections instead of 3. And so what I'm going to be able to do is pick some test points, like let's say negative 1 and 0, and plug those numbers where? Into the second derivative. So when I test these, I'm doing second derivative at negative 1 and second derivative at 0. And I'm only looking to see if these turn out to be what? Positive or negative. So let's see, negative 1 into the second derivative, I get a negative. So that means that my second derivative is negative, which means my original function is what? Concave down, right? Negative people frown. When I plug in 0, I get 6. That's a positive number. My second derivative over here is positive, which means my original function is concave up there. Following?
Yeah, for the double prime, you're using the double prime formula.
Right here. So I plug in negative 1, it comes negative 24 plus 6, that's a negative number. Plug in 0, I get 6, I get a positive number. All right? So can you tell me where I'm concave down? So F is concave. Well, let's do it in the order I asked. Concave up and then concave down. Okay, so where is it concave up? Negative 1/4 and on. Where is it concave down? Negative infinity to 1/4. Yes, negative 1/4. Thank you. Well, no, I'm not asking you to graph it. We're going to look at the graph to verify all of our answers. All right? Next section is called curve sketching, which means we're going to put everything together. We're going to do all sorts, I mean, everything we pretty much have learned, including college algebra stuff, to graph functions. But now we can throw this into it. Graphing by hand is really a pain in the ass, but it brings it all together. All right? So did I answer part C? Okay, what's part D? Do we have any inflection points? Inflection points are anywhere where you change concavity, right? Frown to smile. That happens right here. We have an inflection point. So for part D, inflection point at x is what? Negative 1/4. And then I could actually plug that into the function to figure out where that point is, couldn't I? I'm not going to.
Plug it into the original function.
You could plug it into the original function, which everyone here should be able to do given enough time, right? So what I'd like to do now is I'd like to graph this for us to see if we got close. 4x cubed. Does anybody have any doubt here? Minus 6x plus 1. All right. Where did we say we are increasing? Oh, wait, hold on. Don't tell me anything yet. Let me put a grid in here so we can actually see where these things are. Where did we say we were increasing? Go back and look. Negative infinity to what? Negative 1. See, so my graph goes like this. It's going up until I get to what? Negative 1. And then it's increasing also where? 1/2. That's right here. To infinity. Does it match? Yes. Where is it decreasing? Negative 1 to 1/2. Yeah? That looks good so far. Local max? -1, 6. Local min, 1/2, -3/4. That look good? Okay, what about concavity? It's concave down. -1/4 is where things got interesting, right? And I asked you to plug it in. We didn't. I mean, I said you could, but it looks like it's right around here, doesn't it? And isn't that where the concave down, right, the frown, switches to the concave up, the smile? So we found that inflection point also?
Would the inflection point be midway between the...
It depends on the graph. Yeah, it doesn't have to be. Doesn't have to be. You're talking about, is it in between the max and min? No, it doesn't have to be there. All right? So do you see maybe, I mean, we're still ahead because it's next class, but do you see how you could use all this information to graph it? Right? The things that we didn't get, right, the things that we don't have in this are things like, what are the x-intercepts? Like, where does the graph hit the x-axis? We don't have the y-intercept, right? But those are all things we could get using college algebra. Yeah? Okay. I want to talk, we're going to do another example. We have 30 minutes. That should be enough time for one more example. Is this problem kind of long? These problems are very long, all right? Especially when the functions get more complicated, which I'll make the next one more complicated. But let me talk real quick about the inflection point and why it's important. That problem, not as much as this following one. Let's say that I have number of phones manufactured. I think I spelled that right. If I didn't, I don't really care too much. And then we're going to say here income, money, all right? Let's see here, profit. So you manufacture cell phones, right? That's what your business does. And if you graph this function of the number of cell phones you make versus the profit, it's going to look like something, right? So if you don't make any phones, you're not making any money, right? So maybe we can all agree that this point's here. And then maybe you'll agree that as I produce more phones, I make more money, right? But then there's going to be some point at which I have more phones than I'm selling, right? Yes? And so I'm actually going to not make as much money, and then at some point my profit will actually come down, right? Something like that? Let's just say. Maybe this tapers off towards 0, all right, instead. That might be a good model of what's happening, maybe. Now, we could all agree that this point would be a very important point, wouldn't it? Because that would be the point at which you know that you have the maximum profit, yes? Derivative is 0 there. My function goes from increasing to decreasing there, yes? But this point over here, the inflection point, is also a very important point. Let me show you it right here. This is where we have a change in concavity. All right? Do y'all agree that looks like where the smile becomes the frown? Now, why is this point important in a business model? Let's look at this. Let's look at my slope of my tangent line here. It's positive, isn't it? And it's steep, right? It's not too flat. If I go to the point right here, which let me see, I moved over just a little bit. Here. Whoa, what happened? Okay, so here, slope of my tangent line is something like that. Here, slope of my tangent line is like that. If I actually get on that point, slope of my tangent line is like this. Yeah, you'll see it? Now, the slope of the tangent line represents the instantaneous rate of change of my profit, right? So it's giving me how fast I'm making money. What happens when I get out here? Or on the other side of this inflection point? Am I still making money? Yes? But it's slowed down. See, because my slope, the rate at which I'm making profit is actually slower. than it was back here. Even though I'm still making more money, it's not coming in as fast. And so this point, this inflection point, is called in business, anyone know what it's called? The point of diminishing returns. Diminishing returns. Does it make sense? You're still bringing money in, but it's the point at which the rate at which you're bringing money in is beginning to diminish. Yes? And so we often like to know in a business model where that point is and maybe why it is that way, and then we can investigate further. Because what we want is we want the greatest slope here so that we're making money the fastest. Even though that's where we would make the most money, maybe there's something that we can do to keep this thing steep. So yeah, we'll get to a maximum, but maybe we can keep it steep. Maybe we can move this point of diminishing return over a little bit or something. Right. Yeah. So, or if you have a business model that looks like, this was with the cell phones, but let's say you have a business model that looks like this, where it becomes asymptotic. So you go like this, and let me erase the whole damn thing. So you have something goes like this. So you have like a maximum profit, And somewhere in here is your point of diminishing return. Then it might not be wise for you to manufacture more, because there's some other things that I haven't put into this. This is just the profit, right? It's just, you have to think about your costs too. How much is it going to cost you to manufacture more phones? Well, you're going to need more people, you're going to need more space, more electricity, right? So what you want to do is come up with a model that incorporates all of that. And if you can get your model to somehow get you close to that number, then that's where you're going to have the maximum money coming in. Yeah. So anyway, okay, we can keep going on and analyze this. This is what they do in business calculus. They don't get into the hardcore calculus derivatives and all the limit stuff, but they talk about, okay, look at a function, like where are the important points on the function. And all right. Let's do an example in the last 25 minutes here. So I'm going to go for something a little more complicated. How about all the instructions we just had? Same thing, A, B, C, and D. But let's go with this one. F of x is 5x to the 2/3. You already like it, don't you? Minus 2x to the 5/3. You want to do that? I'm going to do that after the derivative. Yeah. All right, so we want to find where it's increasing, decreasing, local max, local minimums, where it's concave up, concave down, and any inflection points, right? That's what we want. So let's start by just writing out the derivatives. So what's the derivative of this? So 10/3 x to the negative 1/3 minus, is that 10/3 again?
Yeah.
10/3 x to the 2/3. And then I take the derivative of that again. Which is what? Negative 10/9 x to the negative 4/3. Look, I'm bringing the negative 1/3 out. I'm subtracting 1 from that. Minus 29 x to the negative 1/3. I think you can already appreciate the fact that the algebra of this one is going to be much more challenging. Yes? All right, well, let's go with it. So part A, What we're going to do for part A is we're going to figure out where the derivative is 0, and we're also going to figure out where the derivative is undefined. I'm just going to say UND, undefined, all right? That's the two questions we have. Those will be our critical numbers. So let's get our heads around the derivative, the first derivative, because it's not that simple, is it? So let me clean it up first before I do any of this. 10/3. I'm going to write that as x to the 1/3 on the bottom minus 10 x to the 2/3 over 3. That's just rewriting this, right? I haven't done anything else, just rewriting it. Now, for those of you who did your homework on the previous, not mean value theorem section, but the one before it, you know you have to put these in a common denominator, and that usually things get better when you do this. So what's the common denominator that you're going to need here? 3x to the 1/3. So I'm going to introduce on the fraction to the right, what? X to the 1/3 here, and whatever I do the bottom, I must do the top, right? And I'm multiplying that. So this becomes equal to 10 minus 10, and then this times this is just x. All over the common, 3x to the 1/3. That's much cleaner, isn't it? I'd rather set that equal to 0 and find out where that's undefined than do anything else, right? Wouldn't you? Okay, so now let's actually set this to 0. So when I set this to 0, I only have to look at what? The top. The top of that to 0. 10 minus 10x equals 0. And that tells us x is 1. We could all solve that linear equation. And then what about where the derivative is undefined? Is it ever undefined? Where? Whenever the denominator here is 0, right? Which would happen when x is 0. So x equals 0. Now, is x equals 0 in the original domain of the original function? We have to be a little careful with that. Can you plug 0 into this? Because that's not negative, it's not in the denominator, is it? So you don't have division by 0 here, do you? You don't have division by 0 here either. So you can plug 0 into that, can't you? You can plug any number into that, into either one of these. So the domain of the original function is everything, but we're getting a critical number here that can't be plugged into the derivative. So we're going to keep it, right? We're not chunking it. What did I do after this? Not those. Number line. So this is where we have to start to make it can start to get confusing. So from here we do a number line.
Is that still part A or part B?
We're still in part A. What have we answered here? What is this answered for us here?
Where the critical numbers are?
Just the critical numbers. This is just telling us where the derivative is either 0 or undefined. Part A is asking where's the derivative positive and where is it negative, right? This has not answered that question yet. So this is where we need our test points.
So we can use like -1,
Negative 1,
1/2,
1/2. Where are these going to go?
Yeah, part two.
Into the first derivative. That's right. All right, into the first derivative with those. Now, when I plug these into the first derivative, I'm going to plug them into this one because I like this one. This is nice. In fact, I might even go a little further with this. I might just factor that 10 out. Is that all right with you? So I'm going to plug -1 into that. Oh, wait a minute. Hold on. Yeah, -1 will work. Sorry. I almost freaked myself out there. F prime of -1. I thought I was going to get 0 on top. That would have been bad. But I don't get 0, do I? Because negative minus a -1 is really +1. So we get 2 there and 10. That's 20, right? So we get a positive number on top. And then what is -1 here? Isn't that the cube root? What's the cube root of -1? -1. So we get -1 times 3 is -3. So we have positive over a negative, which is negative. Plug in 1/2. And don't assume it's going to switch, okay? Like I said, 1/2 into here. 1 minus 1/2 is still positive times 10. So I have positive on top. What's the cube root of 1/2? Who knows? But it's positive, isn't it? Something times something times something 3 times to come out to be positive had to start as positive. And then times 3. So it's positive on the bottom, which means I have positive. So it did switch. And then what about at 2? So you get a negative on top, and then the cube root of 2 is positive, so you should get a negative here. So it switched, negative, positive, negative. So let's see what that's telling me. My derivative here was negative, which means my original function is going down. My derivative here was positive, which means my original function is going up. And then my derivative here was negative, which means my original function is going down. Now I can answer part A. Where is the function? Where is the function going up? Where is it going down? So this is the answer to part A. F going up, F going down.
So it's going up from 0 to 1,
0 to 1,
going down from
negative infinity to 1,
-1, sorry.
negative 1.
Union.
No, it was 0. Hold on.
Oh, sorry.
It's going down from negative infinity to 0, and then 1 to infinity. Yeah, that's another thing to be careful with. Notice I circled my test points so that I don't accidentally pick them up later and use them for something else. Oops, that's strong today. All right. My college algebra class before this thought I was drinking alcohol last week. They're like, "What are you drinking?" I'm like, "I don't know what the deal was." I seemed to act, I was acting pretty normal to myself. All right, so part B, local max and min. So we already looked at this earlier, but in order to be talking about max and mins, those points have to be in the domain of the original function, which they are. We checked it earlier. So where does it appear that we have a max? Local max at x is what? 1. And what does the value of the function turn out to be there? So we have to plug it into the original function. 1 to any power is 1, so 5. 1 to any power is 1 times 2, so 5 minus 2, 3. That was easy. And then we have a local minimum. Min at x is 0 and f of 0 is 0. Remember, you could write these as points, the point 1, 3. You could write this as the point 0, 0. So we're about like halfway through, right, the problem? The next thing that we need to look at is the second derivative. So we're probably going to need to do the whole process again. So what I'd like for you to take the next 2 or 3 minutes just to see how you do with this. I'd like to see if you can get this and put it together with a common denominator. See, like 2 or 3 minutes, see what you can do while I graph this, and then I'll come back and I'll do it myself. I want to see how y'all are with the algebra. Y'all know what I'm saying you need to do? Do to this what we did to that. Put it together. Okay. See, this graph does not like trying to do that. Okay, because we only have about 6.5 minutes to finish this, hopefully that when you rewrote this, you got what I have here in black. And then realizing that you'd like to have a 9x to the 4/3 as a common denominator, that all you have to do is change that to a 4/3. So you have to multiply by x to the 3/3 so that when you add these together, 1/3 plus 3/3 is 4/3. Now, 3/3 is the same as 1, but just so you see where it came from, right? That's still, this is just x. So this up here, I'm just writing it as an x, but down here is 3/3. So when I multiply those together, I get the same denominator. So I put this numerator, -10 minus 20 times x, and that's it. Do you all see that? Okay. You could factor, yeah, you want to do that? I can do that right now, that's fine. Take a -10 out, and then 1 plus 2x over 9x to the 4/3. All right, what are we supposed to do with that? Set it to 0, figure out where it's undefined. So where's the second derivative equal to 0? Where's the second derivative undefined? Well, where is it 0? You just have to take this piece right here, set it equal to 0, which is -1/2. And then where is this thing undefined? At 0. Right? At 0, you can't plug 0 in here, it's going to go to be undefined. So we have two critical numbers again, right, for this one? So what do I do with those? Number line, right? Make sure they're in order. -1/2, 0. Pick some test points. -1, Negative 1/4. 1. Where do I plug those in? Second shed. I erased it. It was negative 10, 1 plus 2x over 9x to the 4/3, right? Does everyone agree with me that x to the 4/3 means cube root of x to the 4th power? Yeah? Yeah. So this means that who cares what happens here, 4th power, it's going to be positive, no matter what. So on all of these, no matter what I plug in, this is going to be a positive on the bottom, right? Okay, so it's really just figuring out what's happening on top. Negative 1 in here, what happens? Negative 2 plus 1, negative. So that's negative times negative? Positive over positive? Positive. So this means my second derivative is positive here, which means my original function is
Concave down.
smile. Concave up. Now plug in negative 1/4. What's 2 times negative 1/4? Negative 1/2? Negative 2/4, negative 1/2, plus 1? Positive? Times a negative? Negative over positive. So negative? I know that I go through that kind of quick, but I do expect that, you could, given enough time, plug those numbers in and get positive or negative numbers out of it, right? And then plug in 1. Uh-oh. Ah, finally. If I plug in 1, what happens? You get negative again, don't you? Yes. It did not switch, did it? So where is this thing, answering part C, where is F concave up? Where is F concave down? So where's it concave up? Negative infinity to negative 1/2. Where's it concave down? Negative 1/2 to 0. And then it keeps going, right? Notice that it's, even though it's at 0, right, but it's still negative, so it just goes forever.
Could you count on that though? I mean, could it possibly change later?
Nope. Change concavity again? If it does, then we messed up the derivative somewhere. Yeah. It should only change concavity. To change concavity, don't you have to go from positive to negative or negative to positive? Which means you have to go through 0, which means that we missed a solution somewhere if it does it again. Okay, last thing, D, inflection point. Do we have any inflection points? Only one of them, right? X is negative 1/2. And then you could plug that in, right, to the original function to figure out what it is. Okay, so look, I have got 2 minutes left, but let's take a look at this. Can we kill the lights just enough to see this a little better? All right, we had that it was increasing where?
It was increasing.
0 to 1. 0 to 1. Is it going up? Okay. Where was it decreasing? Negative infinity to 0, and then 1 to infinity. Do you agree? Did we have a local maximum? Where? 1, 1, 3? Okay, so look at the scale here. I think this is 2, 4, 6, 8, 10. So 1 and then 3, that's 3. Agreed?
Yes.
And then where was the local minimum? 0, 0. Check it out. That's the local minimum where the derivative was undefined. You see it? It's a cusp on the graph. All right, where is it concave up? Negative infinity to 1. Or to where? Negative 1/2. Where's the negative 1? Right in here? Yeah? Is that right? Yes. Boy, it's hard to see it, isn't it?
Yeah. It does. It looks like it inflects it,
Tell you what I'll do. I'll zoom in. Stop doing that. Stop. Oh, I'm hitting the right instead of the left. Oh, that didn't help. I'm going to try and zoom in here a little bit. What was the value at -1/2? Did we figure it out? We never did. 3.78? Okay, so I'll go to ooh, man, that's hard to see. Boy, that's really difficult to see.
Well, you can see
Negative
it's
point,
concave
well,
down.
I need to go up a little further, hold on. Yeah, you can see it's concave down, can't you? Man, that's hard to see it, but look, at 0.5, which is right here, up to here, right there, we actually have a change in concavity. To the left of this point, it's concave up. It's hard to see it. To the right, it's concave down, but you can see it right there, can't you? It's coming in like this. This is a frown, isn't it? You can kind of pick up the curve right there, can't you? Yeah? Yeah? It looks like a straight line, doesn't it?
Yeah.
That's something you would never be able to pick up with the naked eye that the calculus would pick up, right? Okay, so in there was a change in concavity that we can't even see with our naked eye. And then over here, from 0 to infinity, it was concave down, which is pretty obvious. What do y'all think? It's a lot, right? I mean, we're kind of bringing it all together into something. All right, homework. I would look at page 233, actually 222. I would look at 1 through 7. 25 through 33. All of these, I would look at odds. That's a lot of work right there. On 25 through 33, on these right here, just do parts A through C only. On part D, they ask you to sketch the graph, and we haven't really done that yet. You can try it by hand if you want, but the thing is, next class, I'm going to give you a method for graphing by hand, and I'm kind of particular about the way that I teach it. So if you go do it your own way, next class, I'm going to show you something different. So at your own risk. All right, everyone, do your homework, okay? The most important thing is all the little algebra